Okay, so in this video, we're going to touch on a topic called absolute convergence and how that can help us to solve certain series. Right? So what is absolute convergence and what is absolute convergence and what does it imply about series? Now, the definition. Right, so here, the series A sub n exhibits absolute convergence if the absolute value of A sub n converges. Okay, a series A sub n exhibits conditional convergence if A sub n converges, but the absolute value of A sub n diverges. Okay, so let's take a look here, right, of some examples of both, and let's take a look at alternating series. They lend themselves good to this type of definition, or as examples of this type of definition. In particular, the P series, right? So let's take a look here at the sum -1 n minus 1 over n squared. Right, so if you take a look at this here, squared, right? And then here, so I know that this is a convergent P series. All right. And then we can see here that, so it's a convergent P series because the absolute value of that would just be, all that does is eliminates the plus minus. They're all plus, so it's just 1 over n squared. All right, so it's a P series where P is bigger than 1. And we've proven before in a previous video that this is a convergent series. All right. And we also know by using the alternating series test that both of the conditions satisfy this, right, in the sense that 1 over n squared plus 1, right, that's less than or equal to 1 over n squared, right, because we're adding something to the denominator, making the whole term smaller. And the limit as n goes to infinity of 1 over n squared is 0. Right, so the alternating series also converges. The absolute value converges, so we could say that the series -1 to the n plus 1 over n squared is absolutely convergent. Okay, now on the other end here, we have here the sum of -1 to the n plus 1 over n. So this is our alternating harmonic series, which we proved in the previous video, is convergent. Okay, but we also know that, right, also from previous videos, right, showed up a couple of times here. The absolute value of this, right, again, that just eliminates the alternating part, is the harmonic series. And we know that this one is divergent. Okay, so the absolute value is divergent, while the original one itself without the absolute value is convergent. So this series is conditionally convergent. Okay, so now what can we gain from this knowledge, right? So here, what we can gain here is this theorem here. All right, so it says here that absolute convergence implies convergence. So if you look at the non-alternating part, right, just that value right there, and if that converges, then I can, or not necessarily alternating, but only the positive one, right, the one that has the absolute value, if that one converges, right, then the series itself also converges, A sub n, without the absolute values. Okay, so now how can that be helpful? Let's take a look at an example where we use that theorem here. Okay, so let's say for this example, I'm dealing with the series, the sum n equals 1 to infinity of cosine n over n. Right, and again, we can see that's cosine 1 for 1 plus cosine 2 over 2, plus cosine 3 over 3, etc. Right, now what we notice here is that those values of cosine, it's not even alternating, right? Cosine 1, 2, those are just in radians, so some of them are positive, some of them are negative, right? Again, depending on what the input is, right? So instead, what we take a look at is, well, let me take a look here at this series here. Excuse me. Give me a second here. Okay. Sorry, I wrote down my wrong example here. This is cosine of n squared. All right. All right. And I want to take the absolute value here of n over n squared. Right now, n squared is always positive, so I can write this as cosine of n over n squared. Okay. So here to kind of determine whether this one is convergent or not, I'm going to use a comparison test. Right now, one thing to notice about, or one thing to recall about the cosine function is that the range of the cosine is bounded by 1 and -1. So when I take the absolute value, right, the cosine is actually bounded by below from 0, since it's the absolute value, and above by 1. All right, and then divide through by a positive number. I can write it like this, right? And here we could see by the straight comparison test, this is a convergent p-series. So if the terms of the series are less than the terms of a convergent p-series, then what that tells me here is that here, so again, a reminder, convergent p-series. So then what that tells me is that this is less than that, so the absolute value of cosine n over n squared is convergent, right, by the comparison test. Okay, well, that means that the series here is absolutely convergent, right, since the absolute value converges. So what does that tell me? Referring back to our theorem, well, the absolute value one converges, then this one also converges. So that implies that this cosine n over n squared also converges because of this absolute convergence. Okay, so that's kind of a way of indirectly solving a sequence, excuse me, not a sequence, a series, right, based on its absolute convergence.